Force model workshop. We'll be a bit less formal with the schedule, if we could be less formal. And in particular, we thought it's a good idea to swap Simo and Mike's talk. So Simo's now going to talk at, we had Mike down for an hour and a half. So Mike will be doing the 11 to 12, and then Simo will be doing talk starting at 1:30. Yeah? Okay? Discussion because we can do this discussion. In fact, that can work well because we can do the discussion after Simo's talk after lunch, because I know some people have to leave before the final discussion. So that will give us, we can just move that discussion a bit later. And also lunch doesn't get cold. It already is cold. So we just have to put a guard on it to stop the neuroscientists stealing it. Okay, so well, it's nice to have this workshop. And I just wanted to talk a little bit about, in the welcome talk, use this slot to sort of motivate what latent force models are and how they came about. And actually, in some sense, the story a little bit goes back to this. I found this although now I found this a less worrying talk. There's this guy, Urs, I don't know, is anyone Swiss here or German speaking? How do you pronounce Urs Hölzle? Hölzle. Urs Hölzle, who I think was in Google engineering from the very beginning. So he was really interesting to talk to because he talked about the importance of, I think I had dinner with him or something, because Bernard was program chair that year and I was on the committee or something. And the importance of open source at the beginning of Google. So he was right there at the beginning. But what he was saying at NIPS in 2005, so quite a long time ago, was an emphasis on massive data sets. And we all know this is what Google do sort of very well. Enormous data sets, fairly simple models. And his idea was that, okay, in the future, no NIPS paper will be accepted unless it's running on 2 million data points, which I found rather intimidating because I didn't want to. I had no idea how you ran a Gaussian process on 2 million data points then. Of course, James has fixed that for us in a recent paper, so I'm not worried about that anymore. But at the time, I found that very worrying. So the emphasis was on massive data sets, so let the data do work. More data, less extrapolation. And this is how machine translation works. Relatively simple models of statistical translation, enormous amounts of data. I mean, this is how the whole of Google works. But I found that very worrying because I sort of thought, well, I'm not sure I want to spend a lot of time worrying about the engineering side. Although it's interesting, it's not really our expertise. Although I think we're moving into that now, interestingly. But there's an alternative paradigm to that, which is, the case where you have very scarce data. And I think a good example is, for example, computational biology. You actually get quite a lot of data for computational biology. Thousands of genes expressed at many different time points. But it's very scarce compared to the complexity of what's going on in the cell. I mean, even if you look at E. coli, it's amazing to look at these molecule of the week guy. I can't remember the guy who does it, but he actually has an artist's impression of an E. coli. The complexity of an E. coli, just a very simple organism, is extraordinary. And so even if you've got a lot of data, you've got very little data relative to the complexity of the system you're looking at. And the question is how to generalize in this case from scarce data. And the thought is, well, we need to include more assumptions about the data. We want to put more from a Gaussian process perspective, more in the covariance function. So this is my view of the world. I think that there's, broadly speaking, two approaches to modeling, and I've done a mixture of Gaussians fit to how many people I think are working in these approaches. So data modeling, we might call it statistical modeling. It's pretty much what machine learning people do. And then mechanistic modeling. And mechanistic modeling is more like what Rich talked about the other day in terms of emulation, where people are building simulators of the climate. So I think I've got these points appearing as I go through. So the data modeling paradigm is very much that Google paradigm. Let the data speak. Let's just get a lot of data, throw it at the model. Mechanistic modeling is we impose some physical understanding of the system. So in weather prediction, Navier-Stokes equations, or in Rich's simple example, the gravity dropping things out of the Leaning Tower of Pisa, knowledge of gravity. Data modeling is data-driven, and mechanistic modeling is knowledge-driven. In data modeling, I think of these as adaptive models. So we try and build models that can be flexible and respond to the data they see. But in mechanistic modeling, differential equations are the norm, and differential equations are actually quite rigid about what they specify about what's going on. Classic examples in data modeling is digit recognition and climate weather models are good models for mechanistic modeling. Now, my argument is actually that the origin of all modeling actually started here in the middle. And this split is artificial, and it's also damaging. And we need to be back in the middle. So it's right that some modeling should be here, and potentially some modeling should be here. But the characteristics of this should be in there as well. And the work Rich was talking about in terms of emulation is one of the drives towards that. If you're in mechanistic models and you want to respond to the data, one of the ways you can try and fit your parameters is through emulation. Rich is also doing work on ABC, and I also approximate Bayesian computation, where you just need a simulation and then you can try and do Bayesian inference. And I also would say that's an interesting step from this direction towards that. I mean, the people who first modeled data with mathematical understanding, I think of the era of sort of Laplace and Gauss. And they, I think, would have seen no separation between these two things. They used Newton's laws, and they developed statistical models of noise in order to fit those laws to data. So they were right in the middle. And if you look at the techniques people are using here, and the techniques people are using here, they all go back 200 years to those people, including Bayesian inference. And I think we need to sort of return back and sort of push the communities together. So we've already seen ABC, for those of you at the summer school, ABC and emulation as approaches that pull those mechanistic models towards the data models. And latent force models are an attempt to push adaptive models in the direction of mechanistic models. That's how I see it. Other people may see them differently. Now, the thing is that actually these models are weakly mechanistic. If you make no assumption about your data, then all you have is your data. So when people say, oh no, I made no assumptions, okay, well then you don't do anything. As soon as you start making predictions, unless you're just predicting, responding with what the data point was, you're making an assumption. And one assumption that's very typical is smoothness. So pretty much all non-parametric methods are assuming some kind of smoothness. And I'd say smoothness is a mechanistic assumption. It comes from diffusion. It comes from the physics of the way. Interestingly, heat transfers in the same way as fluids, right? And we all accept that. So we know about the diffusion equation. We know it applies to heat, and we know it applies to sort of fluid movement. But these are physically two very different things, right? And then there's something about, I don't know, the universe perhaps, where there's some regularity in the way the universe operates that comes from underlying maths. Law of large numbers, that type of thing. And that's emergent in properties we see in the world. And then we actually try and include those properties in our models. But they're weakly mechanistic. And I'd say that these models here are strongly mechanistic. So we're much more, here we're imposing sort of weak mechanism like smoothness. Here we're much more rigid about what we're saying is going on in the data. So I'd like to sort of try and do something in between. So we'd really expect a range of models which vary in the strength of their mechanistic assumptions. That's the idea. So instead of having weakly mechanistic and strongly mechanistic, indeed, as soon as you write down a differential equation, actually that's not accurate either, because any continuous differential equation is an approximation to some underlying discrete thing that's going on, probably. So even the models they're using here, they're strongly mechanistic, but they're also incorrect. So this is incorrect and that's incorrect. It's just this is more correct. So there's sort of, everything's fuzzy. It's shades of grey rather than black and white. So the idea in a latent force model is try and add further mechanistic ideas to weakly mechanistic models. And I'll just sort of give a sort of example introduction of how I think that that's possible. So dimensionality reduction, as I introduced yesterday, PCA. Here I'm showing it using slightly different notation. So this is the latent variables, this is the data. So we had this as x yesterday, and this is y yesterday. So y equals xw, right? So this is just dimensionality reduction, and we could assume some noise corruption. Now, as we showed yesterday, if we make this sigma, capital sigma into sigma squared I, and then we have a Gaussian prior over f that's independent across time, then we have principal component analysis. If we make this a diagonal covariance, it turns out to be factor analysis. So there's various models that underpin this. I mean, the reason I've used f and x will become clear in a moment. So for Gaussian priors that's independent, complete independence over f, this is principal component analysis type of model. So we also talked about temporal data. So really excellent talk, I thought, from Simo yesterday about how we can make how the relationship between Kalman filters and Rauktung-Streibel smoothing and Gaussian processes. So if we've got time-based data, instead of having an independent prior over f, we build a prior where it's conditioning on time, right? So now you have a probability distribution of f, where f is multidimensional. This is the latent dimensions. This is like the Kalman filter model I set up. So in the Kalman filter model, as I derived it, then we derived the covariance function here. A bunch of independent latent functions over time. I shouldn't refer too much to the summer school because this is in some sense an independent event. But I did derive this model, right? Effectively the Kalman filter, a simple Kalman filter. But as we said then, using the same trick, now we know that Kalman filters are Gaussian processes, well, we can take the same type of model and do a more general sort of Gaussian process prior. And that's how I motivated multi-output modeling. So traditionally we prefer the Rauktung-Streibel smoother because it's got this linear complexity in n that Simo talked about yesterday. But then there's these advances in sparse approximations, including, I should have added James's recent UAI paper, which make the Gaussian process framework much more practical in general. So we don't necessarily have to constrain ourselves to either temporal data, we can go to spatial data, and that was the sort of direction we're going in there is for multi-output GPs. So that's the sort of, so in fact this semi-parametric latent factor model is in effect doing exactly that. Multi-output GPs are doing that type of thing. They're giving these independent latent processes, and then they're mapping, that gives us these linear models of co-regionalization where the co-regionalization matrix is W transpose that we derived 2 days ago. Okay, but back to mechanistic models. So what's going on in these models? Well, these models are flexible. They're actually really rigid. There's a sort of y equals wx or x is equal to fw in there, which is a very rigid relationship, and we're trying to learn w. But the flexibility comes because we put a probability distribution over f in this case, or x in the latent variable case. So we're getting some flexibility in the model. These latent variables, which are unseen, can respond to the data and do very flexible things. So the model is more flexible than it appears because of putting in this latent variable. So let's have a physical interpretation of what's going on. These latent functions are Q forces, right? So they're not just functions, they're forces, and what we're observing is the displacement of P springs to those forces. So you've got a bunch of springs, and you're pushing against these springs with some unobserved forces, and you're distributing your forces across these springs through a matrix S. So the forces are acting through, for example, a matrix of levers, so distribute across these springs. I'll show a picture of this in a minute. And then you've got these spring constants D, and then you recover the original system because this is just Hooke's law, which springs apparently don't obey unless you pay £20 for them, because I bought a Hooke's law spring and it was very expensive. Regular springs don't obey Hooke's law apparently. This is Hooke's law. And then diagonal matrix of spring constants, and we can recover the original system by setting W equal to these sensitivities, which is how each spring is responding to each force times by this inverse diagonal. So just to hopefully next, a couple of analogies first. So what we're going to do though is add extra dynamical components to that system. So we add a damper to the spring, and we add masses. And this adds extra things. So in general, as I said, we're typically using smoothness. I think a real motivating example that exists in the real world, physics, is inertia. We rarely include inertia in our models, but it's actually all over the place. If I just look out, the reason that these trees tend to oscillate in the wind is because they have mass, right? If they didn't have mass, then they would just move in response to the wind, because the wind isn't oscillating. So you see things around in the world which are resonance due to inertia. If I had a career as a mime, then I would walk around pretending to carry a heavy box, right? And then I have to walk like this, pretending, there's lots of inertia. So you think I'm carrying a heavy box. That's to do with the mass. So certainly including mass seems to be a good thing. I think also, that's the most obvious example of something we don't tend to include in a machine learning model, which emerges in this type of framework. So the idea in latent force models, this is a dynamical second order system, but in general, where you have a differential equation system, you replace some driving force with a Gaussian process. Now, Simo showed us yesterday stochastic differential equations, which are being driven by white noise or the gradient of Brownian noise. I never know and that's actually the same thing. But the Gaussian process in that case is non-differentiable. It's just complete noise. The difference here is that these forces, if we use something like the exponentiated quadratic covariance function, are infinitely differentiable. So that's, I suppose, the novelty here, although I didn't know that much about stochastic differential equations when I started on this area. So basically the idea was just to try and drive. So I was a mechanical engineer, and we used to drive differential equation systems like this with sines, cosines, delta functions, and step functions. Here we're now driving this differential equation with a sample from a Gaussian process. Now, but that could also be, we've also looked at systems with Maurizio that he'll tell you about, where the missing function is an initial condition, where the missing function is just some function in the differential equation that we don't observe. The idea is that that function is now a latent function, and that can absorb this gives you the extra flexibility in the model. A bit like Rich's example of trying to approximate the physical system, but he just added the additional function to the physical system. So he's saying, there's something going on, and then I have to add my latent variable to this deterministic system. Here we're sort of inserting the latent function within the system. Okay, so here's the analogy. So you can try and model, I like modeling motion capture data, as you've seen, and we did it yesterday with the GPLVM. In this analogy, what you'd model it as is like how a marionette tries to reconstruct human motion. So the marionette here has mass on each joint and loose spring constants. And if for realistic motion, the sort of controller, he moves in pretty much, if you've got only a controller like this, 2 dimensions, he puts 2 forces into the system which cause the marionette to move, and then he gets it to sort of do a walk like that. That's the type of idea of the latent force model, that you're observing some high dimensional thing of stuff moving around, but the controlling thing is exploiting dynamics, like the fact that the puppet resonates. He can make it sort of do interesting things using the mass to display a high dimensional data driven by a low dimensional dynamic, 2 low dimensional dynamic functions in the marionette case. So this is to remind me to redraw the next diagram using Tixi. This is the current drawing of this diagram. So this is a sort of analogy that you've got a latent input that you don't see. In this case, it's just one latent force. It's being distributed through 2 pulley systems to 2 mass spring dampers. So we end up having to add in parameters. Well, there's the latent force, F of t, that the man's pulling in over time. There's the observations, the displacements of the mass spring dampers. And then unfortunately you can't see those parameters very well, or those ones. But this basically says that what arrives as the force here is S2 times F of t. What arrives at the mass here is S1 times F of t. We're distributing the force using these pulley systems. And then we have M1, C1, D1, M2, C1, D2. As our parameters of our system. So we've got that, and we need to specify a prior over the latent space. I just put this in 1 minute before I started the talk because actually Martino Barenko's work was crucial in making me think, oh yeah, we can go ahead and do this type of modeling. So I wanted to mention this paper. This was the first, they called it hidden variable dynamic modeling, and they do a very similar thing, but they don't use Gaussian processes. And Martino came to computer science down here and gave a talk at Nick Monk's invite, 2005, so around the same time as that Hutzler keynote talk. And so this is how these things were coming together. And Martino's talk, which was actually a mechanistic model talk, was sort of influential for me. So I just wanted to show that paper and mention that because I don't have time to do the details of that. So what we have now is a driven harmonic oscillator. And actually what Simo was showing the other day is that these things can be solved through solving the differential equations. So these are our state variables x that we're observing, and this is the driving force. And what we can do is we can put a Gaussian process prior over that driving force, in this case exponentiated quadratic. In general, you could put any process prior you want over these things, and then you actually get, sometimes you get existing models, like Markov jump processes. Now this is the cool bit, is this is the type of covariance you get out. So this is the solution for the differential equation, and it's in the form of a convolution. We solve this with Laplace transforms. And this in here is the covariance function, yeah? So the thing is, the nice thing about these convolutions, as Timo was saying yesterday, is that this displacement, xj, must be a Gaussian process if this is a Gaussian process. And the reason is because this convolution is a linear operator. Now, actually, interestingly, this morning I was writing the talk and my son asked me about this sign and this sign. So I tried to explain integrals to him. After I'd explained that, I then tried to explain, he then asked about that, and I said, okay, well, yeah, that's why that diagram isn't finished, because I was explaining integrals while I was, after lying in my bed editing the talk. Of course, but the exact thing that I was saying to him is very important. All I said to him, well, look, this looks very complicated. I explained this, he understood that quite quickly. I said, well, this is a bit more complicated, but actually we can understand it in terms of that very easily. And then I drew a sort of series of boxes underneath the curve and approximated the area, and then I talked about taking the width of the box smaller. And that's what that sign means. That's just a sum, right? You know, so it's nothing complicated. In fact, it means it's really what's going on. When I see that stuff, I'm just replacing that equation there, which says a sum over our Gaussian distributed random variable times a deterministic function. But this function in discrete space just becomes a vector, right? It's a deterministic vector. So this thing is stochastic, and it's Gaussian distributed, and this is, we can think of as a vector. Certainly when we take the integral, that's what's happening, but it's just taking a continuous limit, right? So thinking of it in that way, the sort of key part of that equation is E transpose F, where F is Gaussian distributed and E is just a vector of that sign times the exponential. So actually that tells us that if F is this distributed like this, then X will be distributed like that. Then this is what we've been doing in the talks before. And if you map that back to continuous space, that means that actually you can solve for a covariance function with a double integral. When you map back to continuous space, this says double integral over this deterministic function times the covariance function itself. And Simo was talking about these type of forms yesterday as well. And you get the covariance function out. So this is what it looks like. This section here is just the exponentiated quadratic. And these are the responses. So these are the marginal responses of different mass spring dampers in response to that. But we've specifically made that damping ratio so it's underdamped. This is, I think, overdamped, and this is critically damped. So you get sort of different responses, and particularly note these bands. So this is a negative correlation with what's being put in here. You see the band here is saying, I'm negatively correlated with things that happened before, because the system's exhibiting resonance. So it's going to oscillate. And the width of these bands is associated with what the natural frequency is. But notice there's two bands. This band is similar, but it's not necessarily the same as this, because that's the length scale of the underlying Gaussian process. So you're exciting a system, and then in terms of the way Simo put it yesterday, the system you've got, if we think about this in Fourier space, since we know the exponentiated quadratic, the Fourier transform is something like that, you're exciting a dynamical system with a range of frequencies controlled by, this would be your inverse bandwidth of the, be the inverse length scale in the Fourier space. So you can get some interesting, relatively complex responses by doing that. So this is a joint sample from this covariance. So we sampled the whole thing. So the really cool thing about this is actually, just one slightly interesting feature here. So deconvolution is supposed to be a difficult process, but this covariance matrix encodes deconvolution. So you can deconvolve by just asking what f was given y. So deconvolution is trivial. It's a linear operation once you've encoded it in this covariance. And it's a probabilistic deconvolution. So this is a sort of sample from this system. So the driving function is f of t. The red is the underdamped, the green is the overdamped, and the blue is the critically damped. So what you tend to see is some response. So by hitting the system at the right times here and here, we've actually caused some resonance in red, yeah? But you're not always doing that. Sometimes red is lower. So red is smaller than black here because it happens to be hit at the wrong time, just because of the stochastic nature of these functions. So if you drive these systems with sines, you get very, I think, uninteresting beat responses, that sort of thing. It's not very nice. But if you drive it with a stochastic, smooth, continuous process, then you get these sort of, sometimes the resonant signal is above the driving signal, sometimes it's below. It depends on the stochastics of it being driven. So a couple more sort of samples from that. So for here, for example, black, the driving signal, is typically much larger than red. This is the same parameters of the covariance function. And here, you can see, look, how you get the resonance here. Bang, 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 boo, 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 boo. Yeah? So it's hit it at the right time. It's excited it correctly for 3 cycles, and then you get the sustained resonance of the red. So that's inertia being encoded in a prior. Yeah? Now, when you're modeling, you wouldn't have observed black. You infer a distribution across black. So you observe X, and then you try and use black to reconstruct. So just to finish before handing over to Maurizio, and I have to say that Maurizio is the man for a lot of the work that's here, particularly on this second order system, not so much the first order system. I'll just try and show you a motion capture example, which is actually an example Maurizio put together for our first AI stats paper in this area. Okay, is that? Yep, okay. So what we've got in this motion capture example is some training data of 2 motions of someone doing like a Karate Kid thing. I don't know. People, that ages everyone. How many people here have seen Karate Kid? I mean, I think I saw it when I was 14. So these are motions from the CMU motion capture database, 2 motions. And the idea was to train the latent force model on this. And the way we're training it is estimating at every joint mass and a spring and a damper, right? So we estimate the weight of each joint, and then we estimate the spring constant and damping coefficient. In fact, we don't quite do that because that's over-parameterized. So you actually estimate something closer to the natural frequency and the damping ratio or coefficient, whatever it's called. So take those 2 motions, and what we wanted to do is sort of predict on another motion. I've got some results from that, which I probably won't show. But the point was that the next motion was, maybe I will briefly show the results. The test data is actually, it's the same sort of motion, but the action he takes is much more extreme on the arm movement. So it's a sort of extrapolation prediction that you're trying to make here. I'll probably just show briefly the slide of where we try the extrapolation. But what I wanted to show really in this demo is how we can now sort of simulate this data in that puppet-like way. So what I have here, try and reset these window sizes a bit, is like the puppet. This is like the marionette control. and this is the marionette. So this is different to the sort of visualization I showed yesterday with the GPLVM, because the marionette control is dynamic. The puppet has to respond to the dynamics of what you do. So what I'll do is I'll run a trace through here, and you'll see the arrows will try and represent the dynamics of the trace. I have to click once, run the trace, click once, and then it will take that trace and feed it through the model. So it won't move in real time. What we see here is the latent forces the model's using to predict the training data, motion 18 and motion 19. Yeah, so these are the two latent forces that it used to create the training data. And I hope to persuade you that we get some nice extrapolatory effects. So here's a sort of reattempt to create the training data. But I actually went backwards as well. So what do we manage to do is actually make the man step back as well. Now you need the physics to do that. Nowhere in the training data did he move his leg backwards. That's because you've put in a differential equation that says we're driving by a force, so if you reverse the force, was that a question or was that a...
Question.
Okay, yeah, question.
In terms of learning here, what you've done is to learn a whole lot of masses, damping coefficients, and
spring constants. And latent length scales. Yeah.
So it's a whole lot of covariance function parameters.
Yeah, that's a good question because I didn't make that clear.
Pardon? That's what we've learned is covariance function parameters.
And then you've learned, so that's good. Thank you, James, actually. So, and in fact, the hierarchical GP stuff we did is inspired by these examples because we could do it better. But what, James' question, all you've done here is learn covariance parameters. Yes. And what we've done is we've taken two motions and assumed they're independent given the covariance function parameters. So we're making a block diagonal assumption between the two motions and assuming that the dependence is only through the fact that this man has the same mass springs and dampers across each motion. What we should do is the hierarchical GP thing that you've done in computational biology, where you actually perhaps assume that there's some shared motion overall, and then there's some way in each individual motions depart from that, but we didn't implement that. But I think that would be a really good way of fitting this data. But we're assuming these motions are independent apart from the masses, springs, and dampers in the model. Yeah, thank you.
Did you know the kinematic chain of this? Do you assume anything about it?
Do we know? We assume it for visualization, and the data is presented in the form of angles. So we don't know anything about, so just to show that we don't know anything about what knees can physically do, let's try and see what happens if we just, in fact, look, we can try and go off the plot, right, and put some forces in. See what this does to his knee. Ow. Okay, so it doesn't know, like it will extrapolate in regions of, so this is no force, so you shouldn't move much there. But it knows the angles, it knows the channels to model, which are the angles, and then the reconstruction of the skeleton is putting angles back into a skeleton model. So it's not modeling, yesterday the models I showed you were actually modeling an XYZ space, so the feet could become distended. Here it can't because the model is the angle between this joint and this joint, well, the two angles. Some of them have two angles, the knee has one angle, I think. Rather than the XYZ positions.
Is that what you use as input to your training?
Yeah, that's what we train on. All the angles. So there's about, I don't know, 30 or 40 of them or something like that,
yeah. So for your covariance matrix and the length scale, you actually use the training data to get the data.
Yeah.
And then rest the data, then you predict the motion.
Yeah, well, I haven't shown you any prediction yet. I'm just showing you simulating, from the, I'm getting called for time, simulating from this model. So, and the other thing I just wanted to show you is actually not much happens in this dimension. Not much apparent, but actually I think something's happening on the end of these hands, which I'll show in a moment before I finish. But yes, I haven't done any prediction yet, but this is just trained on those two motions. So the argument is we could do better extrapolation, and I'll just finish on a slide and then maybe take questions while Mauricio sets up. I can't move my mouse there. This is a slide, actually this is a reduced version of that problem where we just try and predict one arm. So here we've got the various angles in our arm, which is the wrist, hand rotation, thumb rotation, X rotation, hand rotation, Z rotation, all these angles that are just in the arm, and across the motion 20. And the way we do that is we have as inputs the 3 shoulder joint predictions. So we treat them as, we've got the conditional, because it's a joint model of the outputs, we can condition on these 3 joints and say, given these 3 joints across time, condition on time and these 3 joints, which are actually all on the outputs, but we're saying we observe these 3 outputs, and because there's correlation between the outputs, we can make a prediction about what the other outputs do. So we've got like 3 inputs here and the arm moves. The reason we want inputs is because we compare with a Gaussian process regression, trained on the training data, where the inputs are these 3 angles and the outputs are the target angles. But that model doesn't have any knowledge of time, so it can only make predictions at individual points. It can't make a continuous prediction. And what's interesting is, of course, that it also doesn't know about the dynamics. So these effects here, these wiggle effects, is to do with the fact that the arm wobbles. And although it does wobble in the training data, it wobbles, the arm motion's quite different. And actually all that happens to the Gaussian process, I don't know if you can quite see it, the error bars saturate. It's just saying, I've never seen data like this before. I don't know anything. Because it's trying to extrapolate, and it does the right thing for a GP to do. Its error bars are too small, but it does the right thing for a GP to do. It just saturates its error bars. Whereas the latent force model picks up those sort of things because it says, well, clearly there was some sort of input there and I should have a resonance. Even though I've not seen that type of input before, I know the response. So extrapolation becomes interpolation, yeah, because it understands inertia. And that's the principle. I mean, it could be whatever physics you put in. It could be various different physics. But that's the principle behind the latent force model, as the way I see it, is that by putting physical knowledge in, you take extrapolation and you make interpolation. And by putting that extra knowledge in, you can use less data to predict the system. And I've overrun by 10 minutes, apologies. So pass to Maurizio and maybe take questions about that while Maurizio sets up. Any questions?
Just a very simple question. So the term latent force models is just, can I treat it as a Gaussian process, a model that combines both the physical...
Sorry, I missed that because of the door closing. Combines
both the physical laws and the data.
Yeah, I mean, that's the idea. But I suppose there are other approaches that are also doing that. What I take it to mean is a physical model where you use a process prior over some unseen state of that physical model. So there are many examples of this exist which aren't called latent force models. So maybe I'm being too general. The specific things we've implemented are Gaussian process priors, or as I think Maurizio is going to tell you, switching Gaussian process priors, which to allow discontinuities, to drive ordinary differential equations and I guess stochastic differential equations. So I don't know, how catch-all you can use the term to be, but to me, in the context of Gaussian processes, it's just a way of building a covariance function that has all these mass spring damper parameters, has physical parameters in. Rich talked about in his talk on Tuesday that if we've got physical knowledge, we could include it in the mean function. And I don't like that. I mean, maybe I'm wrong to not like that, but I prefer. So, and that's the sort of physical knowledge Rich means, I think, that you understand it's a differential equation or something like that. But I think that puts too much faith in these strong mechanistic models. I mean, it's correct sometimes, because strong mechanistic models are good. So it's just a matter of taste, perhaps. But the objective with latent force models is to make those mechanistic assumptions weaker, like the smoothness assumptions that we use in, or that was my objective. I mean, everyone's entitled to see them in however way they like, but yeah. Other questions? I think Maurizio's ready to go. Do you want to do a battery change? Okay.
Can you see